So good afternoon, everyone. We are going to start with unit number 5, that is control system, and thereafter we'll follow it with the stability part of control systems. Now, friends, as we all know, we have been discussing about mechatronic systems. We saw the generalized block diagram of a mechatronic system. We studied sensors and transducers, and thereafter we studied some actuators, and prior to that we studied some signal conditioning devices as well. Now the next part of our curriculum leads us to study of conventional control systems, modern control systems, and its applications to mechatronics as such. And thereafter we'll be continuing with our studies with microprocessors, microcontrollers, and programmable logic controllers. So this is how our flow would be. Now, as far as this unit number 5, control systems, is concerned, as you all know, this is a field in itself. Control systems, automatic control engineering, or control systems. As I told you earlier, in most of the IITs and NITs, there is a separate discipline called as systems engineering discipline, wherein there is a full-fledged curriculum of control systems. Now, these control systems are of relevance not only to mechanical engineers. These are relevant to electronics and telecommunication engineers as well. These are related to computer scientists as well. These are related to civil engineers. So in a true sense, this control systems field or systems analysis field is multidisciplinary in its approach. So in most of the Western universities and most of the IITs and NITs, this subject is offered to students of all the disciplines, because when we study our conventional engineering practices, as far as our mechanical engineering is concerned, we study some subjects related to design engineering, we study some such subjects related to manufacturing engineering, and we study some subjects related to thermal power engineering. And thereafter we look for the applications of these basic subjects in the field of mechanical engineering. Similarly, each discipline students, they study their core curriculum, and they try to apply those fundamental principles to design of various maybe electronic systems, mechanical systems, or mechatronic systems. Now, while doing so, there is an important aspect common to all the disciplines. That aspect is design and development, or research and development. So this is common in civil engineering, mechanical engineering, computer engineering, and electronics and telecommunication engineering. It is a common discipline in a sense. A mechanical engineer designs a product, develops a product. An electronics engineer designs a product, develops a product. Similarly, civil engineers or transportation engineers, they design certain civil engineering systems. Some civil engineers going for design of irrigation systems, development of irrigation systems. Some civil engineers going for maybe remote sensing applications. So likewise, each discipline goes in for design and development of products and services. Now, the important step in any of the design and development activity as such, it is not that the product is manufactured directly. The idea is stuck to my mind and I started manufacturing the product. No. What we need to do is a lot of brainstorming is done before a product is developed. The drawings are made, and then before making the prototypes, the basic analysis of the system is needed to be done. Suppose, for example, I want to develop a turbine, let us say, a hydraulic turbine for power generation application. This is the assignment as a design and development engineer or research and development engineer entrusted on me by the authorities. What I do is I first of all analyze the available resources. If I'm talking about a hydroelectric power project, what is the head available? What is the water quantity available? What are the geographical constraints? And thereafter, I identify what are the critical parameters, like what is the maximum head available. If the maximum head is available compared to the maximum quantity of water that is available, I look for some impulse type of a turbine, development of an impulse type of a turbine. If I got moderate head and moderate quantity of water, I go in for a Francis type of a turbine or a turbine similar to that. If I got less head and large quantity, this is the case with our Ujni Dam. We don't have high head. If you have visited Ujni Dam, we don't have high head available, but we have got abundant quantity of water that is available. Then I'll go in for some axial flow turbines or maybe Kaplan turbines. So why I'm telling you this is I'm trying to conceive the idea of a development of some hydraulic turbine for my power generation application. What I do, I have conceived that idea. I know the figures, facts and figures. I build the model. I want to develop an efficient hydraulic turbine. Efficient in the sense the conversion efficiency from hydraulic energy or mechanical energy to electrical energy has to be maximum. I try to develop, I think of the various parameters, and then I do the analysis. What is the what should be the geometry of the blades? What kind of turbine it should be? Whether it should be an impulse type of a turbine, whether it should be a reaction type of a turbine, or whether it should be a mixed type of a turbine. Whether I should develop a different type of a runner, so to say. Whatever I'm planning in my head, in my brain, I'm thinking, and once I decide, yes, I'll be going in for this type of mixed type of a turbine. Then I jot down, I draw a sketch, a conceptual sketch. I prepare an assembly drawing. We are still on paper, remember. I develop an assembly drawing. I develop a component drawing, so to say. And then I select materials, appropriate materials, depending on the salinity of water and the turbidity of water. What material will be most appropriate? What would be the pressure variations? What would be the velocity variations? Keeping all these things in mind, I select the material. Remember, we are still on paper in the development phase. Then I prepare a drawing, assembly drawing, component drawing, and then I do the analysis of various components. What would be the pressures? What would be the forces coming on the turbine runner, turbine blades, and what should be the dimensions based on my strength requirements. Here, not only static strength is important, dynamic strength also I need to think of and I consider. Then on paper, I prove that the design is safe. Hello? Ah, ah. एक 5 मिनिटांत माझं लेक्चर चालू आहे. एक 10 मिनिटांनी बोलेन. So I select the material, I define the dimensions on paper, and then okay, on my paper the design is ready. I use a finite element analysis software and I prove that the design would be safe, fail safe, and then when it comes to performance analysis. Now, for performance analysis, I had to first of all, maybe I have to build a prototype. I have to install that prototype on the site and then see at various head levels how much is the RPM that I'm getting, how much is the power that is generated I'm going to get. This used to be the conventional practice earlier. Now, for the past 3-4 decades, people have focused more on simulated testing. What they do is, before going in for development of a prototype for any product for that matter, let it be a kitchen product, let it be a domestic product, let it be electrical component, let it be mechanical component, any component. I just told you one example of a turbine, water turbine example. So before I build a prototype, physical prototype, what I need to do is, once I decide the dimensions, what I do is I subject that geometrical model to various types of dynamic situations, so to say. So for that, nowadays there are many softwares available. But somewhere there, this subject of control systems fits into the scheme. What we do in control system analysis, what we do is, once I prepare a geometrical model, once I prepare a conceptual model, once I define the dimensions, once I set the parameters, before I build my first prototype, what I do is I develop a mathematical model describing the dynamics of that turbine working. What do I mean by that? See, that turbine, hydraulic turbine, will be receiving some input and it will be giving out some output. What is this? It is receiving a pressurized fluid, pressurized water. That pressurized water is entering into the turbine casing. It flows over the runner blades and then it starts developing mechanical power. So what has happened? Input is pressurized fluid and output is mechanical power. It is generating certain power. At certain RPM, it is developing certain torque. The runner or the output shaft is generating certain torque. So output is power, mechanical power. So some input is there and some output is there. And in between this input and output, there is a system called as a turbine system. It has a definite geometry, it has got definite mechanics defining, maybe a momentum equation is involved, Bernoulli's equation is involved, and then some mechanics aspects of conversion of energy are involved, friction is concerned. So I consider all these aspects, and what I do is I correlate. Remember, I'm still on paper, I'm not developed physical component as such. What I'm doing is I define the input and I know the output, and in between, whatever are the processes those are happening. Maybe in steam turbines those would be thermodynamic processes, in hydraulic turbines it would be fluid processes. Similarly, based on the fundamental principles of thermodynamics, heat transfer, or fluid dynamics, I know the correlations between input and output. The kinetic energy is converted into some mechanical energy. Kinetic energy in the fluid is getting converted into mechanical energy. I know the underlying principles which are followed in between, within the turbine. So what I do is I develop a mathematical model describing the dynamics of this hydraulic turbine system. Then once I build a model, I build a transfer function which is similar to my efficiency. Only thing is that the major difference is that in efficiency, the output by input, efficiency is the ratio of output by input. The output unit and the input unit are same in case of efficiency. Output power by input power, that is power efficiency. Output heat, input heat, that is thermal efficiency. The units are same in case of efficiency. Whereas in control systems, what I build is I develop output by input relationship, fine. But the units of the output and input need not necessarily be the same. So what I mean by that, in case of this hydraulic turbine, what is the output? Output is mechanical power. Okay, some watt of mechanical power. And what is the input? Input is some kinetic energy or flow energy, maybe some quantity of fluid. So fluid flow and is the input, and output is mechanical power. And what is the transfer function of this turbine system? It is output by input. So mechanical power divided by fluid flow. The units are not same, and that's why the name transfer function is given to that, because this fluid flow is getting transferred or getting reflected into mechanical power. So this is how I build a mechanical mathematical model for my turbine system, and I subject this mathematical model to variety of input parameters. Remember, I'm still on paper. What I do is now this turbine, once I have built a mathematical model defining the dynamics of my turbine system, what I do is I think of various situations where there will be power fluctuations. Now, in case of hydraulic turbine, what would be the variations in input? If the reservoir, the dam, so to say, the water level is dropping, that is the head is dropping. For different heads, how much will be the power developed? I want to assess that. What I do, I have got this input-output model. I input the reference head, and I can predict, I can solve the differential equation of operation of this turbine, and I can predict how much would be the mechanical power. So I'm predicting the performance of this turbine system by using mathematical modeling. Then this is one parameter. And then flow rate variations. I can simulate those flow rate variations by just changing the inputs. And I see how much will be the power fluctuation. Then what will happen? Now this turbine assembly would be connected to some electrical generator. Now this electrical generator will be connected to a transformer, and then this transformer will be distributing power to different industrial establishments and maybe domestic purposes. Now there will be load variation. Okay, my dam has got sufficient water, sufficient power I can develop. But right now, on the output side, the load is not that much. Okay, so I need not waste my generating capacity, isn't it? So the load is less. Accordingly, I need to develop lower power. Now I can simulate this situation also through my mathematical model. I can just modify some parameters in my mathematical model, load variation parameter, and corresponding to that, how much should be the fluid flow that should be maintained, so that my turbine and generator assembly would develop the requisite power for my application. Now, this is how I can predict the system performance before the first prototype is built, isn't it? So, this is one use, one application of mathematical modeling. Now, this is one of the aspects of control systems engineering. Even in case of mechatronics system, why it is included in mechatronics curriculum is that I'll be developing some mechatronics device, maybe engine control system I'm developing, which is a pure mechatronic device, which will be controlling the RPM, which would be controlling the torque developed, which would be controlling the fluid mass flow rate, which would be controlling the temperature of various parameters, which would be controlling the pressures within the system. Now, in such a mechatronic system, I can utilize, I can use the principles of control system. I can build a mathematical model for my mechatronic device and subject that mechatronic device for a variety of input conditions, and I can predict the performance of this mechatronic device for further applications. Now, suppose I have developed one robot which is catering to the needs of industry, like a welding robot. Before I practically physically develop a first prototype or physically develop a first product, robot, what I need to do is I need to develop a mathematical model describing the dynamics of that robotic application. And then I'll be subjecting that robotic application mathematical model to variety of input-output conditions, and I would be predicting the performance. Now, what is the use of predicting the performance? Thereafter, I can suggest certain modifications in the design. For these load conditions, these would be the changes required. For these input conditions, these are the changes required. So I can come out with the best possible design of a product or service. So this is the main use of predicting the performance of any system, so to say. So this is how control systems play a very important role in the design and development of even mechatronic systems. We'll discuss few more things about control systems and its applications in the next lecture. We'll stop for today.